In this section we discuss elastic deformation, starting with stretching, compression, and Young's modulus. We have seen that a spring returns to its original shape when the force compressing or stretching it is removed. In fact, all materials become distorted in some way when they are squeezed or stretched, and many of them, such as rubber, return to their original shape when the squeezing or stretching is removed. Such materials are said to be elastic. From an atomic viewpoint, elastic behavior has its origin in the forces that atoms exert on each other, and these forces can be symbolized as springs. It is because of these atomic-level springs that a material tends to return to its initial shape once the forces that cause the deformation are removed. The interatomic forces that hold the atoms of a solid together are particularly strong, so considerable force must be applied to stretch or compress a solid object. Consider a force that pulls on a circular rod and stretches it. This, by the way, is called a tensile force when directed this way. It would be a compressive force had the force been oriented in the opposite direction. Experiments have shown that the magnitude of the force can be expressed by the relation F equals y times delta L divided by L0 times A, provided that the amount of stretch or compression is small compared to the original length of the object. In this equation, F denotes the magnitude of the stretching force applied normal to the surface at the end. A is the cross-sectional area of the rod, delta L is the increase in length, and L0 is the original length. An analogous picture applies in the case of a force that causes compression. The term Y is a proportionality constant called Young's modulus, after Thomas Young, who lived from 1773 to 1829. Young's modulus has units of force per unit area, or newtons per meter squared. It should be noted that the magnitude of the force in this equation is proportional to the fractional increase, or decrease, in length, delta L divided by L0, rather than the absolute change in length, delta L. The magnitude of the force is also proportional to the cross-sectional area A, which need not be circular, but can have any shape, for instance, rectangular. The table gives values of Young's modulus for some common materials, all of which are in the 10 to the 9th to 10 to the 11th newtons per meter squared range. It gives you an idea of the relatively large magnitudes of forces that are required to stretch most solid materials. It is possible to deform a solid object in a way other than by stretching or compressing it. For instance, consider applying a force parallel to the top surface of a block of gelatin. Notice that the top surface and the material below it shifts relative to the stationary bottom surface. The resulting deformation is called a shear deformation and occurs because of the combined effect of the force F applied to the top surface and the force negative F applied by the plate to the bottom surface. In general, shearing forces cause the solid object to change shape. In the drawing, the directions of the forces are parallel to the surfaces, each of which has an area A. These two forces have equal magnitudes but opposite directions, so the gelatin block remains in equilibrium. The magnitude F of the force needed to produce an amount of shear, delta X, for an object with thickness L0 is given by F equals S times delta X divided by L0 times A. This equation is similar to the one for Young's modulus. The constant of proportionality, S, is called the shear modulus and, like Young's modulus, has units of force per unit area, or newtons per meter squared. The value of S depends on the nature of the material, and the table gives some representative values. When a compressive force is applied along one dimension of a solid, the length of that dimension decreases. It is also possible to apply compressive forces so that the size of every dimension, length, width, and depth, decreases, leading to a decrease in volume. This kind of overall compression occurs, for example, when an object is submerged in a liquid, and the liquid presses inward everywhere on the object. The forces acting in such situations are applied perpendicular to every surface, and it is more convenient to speak of the perpendicular force per unit area rather than the amount of any one force in particular. The magnitude of the perpendicular force per unit area is called the pressure. The pressure, P, is the magnitude F of the force acting perpendicular to the surface divided by the area A over which the force acts, or P is equal to F divided by A. The unit of pressure is Newton per meter squared, which is called a Pascal. Even though the magnitude of a force is included in the equation for pressure, pressure is a scalar quantity, not a vector quantity. Suppose we change the pressure on an object by an amount delta P, where delta P represents the final pressure P minus the initial pressure P0, or delta P equals P minus P0. Because of this change in pressure, the volume of the object changes by an amount delta V equals V minus V0, where V and V0 are the final and initial volumes, respectively. Such a pressure change occurs, for example, when a swimmer dives deeper into the water. Experiment reveals that the change delta P in pressure needed to change the volume by an amount delta V is directly proportional to the fractional change delta V divided by V0 in the volume, or delta P equals negative B times delta V divided by V0. This relation is analogous to those for the shear and Young's modulus, except that the area A in those equations does not appear here explicitly. The area is already taken into account by the concept of pressure, magnitude of the force per unit area. The proportionality constant B is known as the bulk modulus. The minus sign occurs because an increase in pressure, delta P positive, always creates a decrease in volume, delta V negative, and B is given as a positive quantity. Like Young's modulus and the shear modulus, the bulk modulus has units of force per unit area, or newtons per meter squared, and its value depends on the nature of the material. The table gives some representative values of the bulk modulus. In summary, we have examined the equations that describe stretching and compression, shear, and volume deformations. In all cases, the degree of deformation was directly proportional to a modulus, Young's, shear, or bulk, that is a constant property of the material being deformed. We defined the pressure as the force per unit area. The moduli, Y, S, and B, as well as the pressure P, all have units of newtons per meter squared.